Hello everybody, welcome to a session where we're going to summarize the entire chapter on metals and non-metals for class 10 CBSE. As you all know that this is an important chapter and carries adequate weightage on your board exams. So it is necessary to have a summary video where you could just go through it a few hours before your exam or even on the way to your school while you're at your exam, because last minute preparation always helps you do much better and get good grades in your exam as well. Now in this summary video, we will be dividing the chapter into two parts. The first part is all about properties of metals and non-metals, and the second part is the entire metallurgical process of extraction of metals. Now to begin with, we all know metals are elements of the periodic table that are excellent electron donors, which means you take a metal such as sodium, potassium, lithium, copper, mercury. All these are excellent electron donors, so they automatically become metals, whereas non-metals are those that are electron acceptors. These are elements that have a tendency to accept electrons, which would be oxygen, nitrogen, chlorine, bromine, fluorine, and all of that. The first part of the chapter, we shall talk about their physical properties, mostly around their luster, malleability, ductility, tensile strength, sonority, and all of that. And then we'll move into their chemical properties. So to start with, let us try and understand what their physical properties are going to look like. So I'm just going to divide the board into two parts so that we could discuss metals, non-metals together. The first thing is, let's talk about a property called as luster. Luster basically means an outer shiny appearance. Metals generally have an outer shiny appearance, whereas non-metals generally do not have a shiny appearance. However, there are few exceptions, and I'm going to put those exceptions here. Except diamond. Diamond, we all of us know, shines. You can also think of graphite. Iodine as well has a lot of shine on its outer surface. There are certain metals that may not have a very good shine. For example, lead doesn't shine too much. But apart from that, most of the metals do have a shine of their own. However, you need to also understand that metals, highly reactive metals such as potassium, sodium, etc., may not appear to be shiny because they easily get corroded due to their exposure to oxygen, but they're so soft that when you cut them with a knife and when you open it, it shines like a mirror. So all these metals that may not look very shiny from the outer surface due to corrosion actually look shiny when you open up and see them. The next one is malleability. Malleability, all of us know, is beating them down into thin sheets. Metals are highly malleable. Whereas non-metals are mostly non-malleable. However, you need to understand that all the soft metals that we think about, it could be mercury, it could be potassium, sodium, lithium, all of them being soft can't really be malleable. So if you try to smash them into tin sheets, they're so brittle that they break into powder. Alright, so I'm going to put exceptions here, except sodium, potassium, mercury, calcium, etc. Similarly, we all know about ductility. Ductility is the phenomenon with which you can draw them into thin wires. I'm just putting keywords here. Again, exceptions are the same. You cannot really draw metals such as sodium, potassium, mercury, calcium into thin wires. You can't because they're so soft. One, you cannot touch them with your hand. You cannot touch sodium, potassium directly with your hand because it can burn your hand. So you can't really draw them into wires either because they're so soft, they'll just break if you try to draw them into wires. Similarly, when you look at non-metals, they're non-ductile. However, carbon under certain conditions can be made into carbon fibers, which are carbon wires. So some books do give that as an exception, but I feel you could just say non-ductile for all metals. If you want to look at carbon as an exception, you can. Now let's look at sonority. Sonority is where it makes a characteristic sound when you drop it. For example, when you are ringing the temple bell, or if you drop a key on the floor, or if you have a metal strike against another metal, you get that characteristic sound. That is called sonority. all hard metals tend to be sonorous. Soft metals cannot be sonorous. So the exceptions will still be the same for you. Sodium, potassium, mercury, calcium, all of these are non-sonorous. The keyword that you need to write is the characteristic sound. Alright, whereas these are definitely non-sonorous. Let's look at a few more properties of metals and non-metals that are different from each other. Here we have metals, here we have non-metals. Let's look at tensile strength. Metals generally have high tensile strength. Tensile strength is the ability to withstand stress, or when you apply very high pressure, it shouldn't really break. However, there are metals such as sodium, potassium, etc. that are quite soft, that are not very firm. So if you try to apply too much pressure, it can just break. Whereas non-metals generally have poor tensile strength. So if you take phosphorus for example, the best place to get red phosphorus is on the tip of your matchstick. All of us know that if you just press the tip of the matchstick, it breaks very quickly, which means it cannot have very high tensile strength associated with it. We also know that metals are great conductors of electricity as well as heat. Whereas here they are poor conductors. Graphite is an exception, and we all know why graphite is an exception, because it is bonded only to 3 more carbon atoms, which means the 4th bond is available for conduction. That is why it causes some form of heat conduction. So I'm going to write graphite here. We also know metals have high melting and boiling point, and non-metals have low melting and boiling points. You could take a screenshot of this, or you could quickly summarize it so that it becomes easy before you go for your examination. Now that we have understood all the physical properties of metals and non-metals, let us move into some of their chemical properties. Now when it comes to metals, metals have so many important chemical properties. The most important ones of them is going to be reaction with oxygen. Second one is reaction with water. Third one is reaction with acid. Fourth one is reaction with chlorine gas. And the fifth one is reaction with hydrogen gas. Now when it comes to reaction with oxygen gas, high reactive metals such as sodium, potassium, etc. can easily get corroded in the presence of oxygen to give you its metallic oxide. So sodium plus oxygen gives you sodium oxide, potassium plus oxygen gives you potassium oxide, and so on. If you take calcium and magnesium, they also give you calcium oxide and magnesium oxide. However, it is advisable that since these two are moderately weaker than these two, it's advisable that you apply a little bit of heat for the reaction to take place. Similarly, if you take something like aluminium or iron, aluminium will react with oxygen to give you aluminium oxide. Iron will react with oxygen to give you Fe2O3 under circumstances, or Fe3O4 depending on how much oxygen you are supplying. Fe2O3 is called ferric oxide, Fe3O4 is called triferric tetraoxide, or it is also called as the magnetic oxide of iron. Now even for these, because they are less on reactivity, you can also heat the reaction for the reaction to take place. However, if you take very low reactive metals such as copper, copper also tends to react with oxygen, but you need to heat it for a prolonged period of time. And what happens to copper is, after a long period of time, copper turns into copper oxide, and you need to know that copper oxide is black in color. It is jet black with an amorphous texture. So copper reacts with oxygen to give you jet black amorphous copper oxide. However, since it's poor on reactivity, you need to keep heating it for a long period of time. Now let us look at how it works with water. Here again, if you look at all the highly reactive metals like potassium, sodium, etc., they tend to react immediately with cold water itself. If you look at metals such as calcium, magnesium, they tend to react with warm water. But if you look at elements such as aluminium, iron, etc., they tend to react only with steam. So let us see how these reactions are going to take place. I'm just going to erase this. You have made a note of it. And let's work with water. Now when it comes to water, potassium, sodium will immediately react with cold water because they are highly reactive to give you their metallic hydroxide. So metallic hydroxide for potassium is KOH, the metallic hydroxide for sodium is NaOH, and both will release hydrogen gas. So how do you test for hydrogen gas? You just bring a matchstick to the mouth of the test tube, the matchstick goes off, the fire goes off with a pop sound. If you take moderately reactive metals, when I say moderately, not very highly reactive, nor are they very poor in reactivity, take calcium and magnesium, you can make them react with warm water. These two produce their hydroxide, so calcium produces calcium hydroxide, magnesium produces magnesium hydroxide, and both will as usual liberate hydrogen gas. However, there are few important observational changes you will observe with respect to these elements and these elements. Since these are strong, when you put a piece of sodium or potassium inside water, cold water, it makes a buzzing sound on the outer surface. It can catch fire, sometimes it can explode, and it constantly releases hydrogen gas. And the solution eventually turns alkaline because KOH and NaOH is formed. However, when you take calcium, when you drop calcium, calcium first sinks inside because of its higher density, then it gets surrounded by these hydrogen molecules. That makes it light, it rises to the surface, and then it creates a buzzing sound to liberate hydrogen gas. So know the difference, calcium first sinks, sodium and potassium do not sink, they just go on the outer surface itself. Now let us look at metals that are quite weak. If you take iron or if you take aluminium, they generally don't react with cold water nor hot water. Instead, it's best that you heat these and pass it over steam. Steam also has the formula of H2O. The only difference is you'll write H2O gaseous. This is going to give you its respective oxides. Now that's the difference. These two will give their hydroxides, these two will give their oxides. So you're going to get Al2O3, you're going to get Fe3O4 plus you're going to get hydrogen gas. I told you Fe3O4 is also called as magnetic oxide of iron. So you can call it triferric tetraoxide. You can also call it ferroso-ferric oxide. Alright. And finally, if you look at the metals much below, like copper or mercury or silver and all of them, they hardly react with water. So they generally don't react with water. The same thing is true even for oxygen. Mercury can react with oxygen to give you mercuric oxide, which is orange in color. But if you look at silver and gold and platinum, they don't react with oxygen under any condition. I hope all of you have made a note of this. Let's move into reaction with acids now. When it comes to reaction with acids, I'm just going to clear this again. The reaction with acids is also going to be very similar to reaction with water. It depends on what type of acids you're going to use. Under this, we're going to classify them into two types of reactions. One is reaction with HCl and H2SO4, and the other one is reaction with HNO3. Now, HNO3 will not react with HCl and H2SO4, primarily because HNO3 is an excellent oxidizing agent, whereas HCl and H2SO4 will cause simple displacement reactions to take place. For example, if I take a strong metal like sodium or potassium, if I make it react with HCl, which is hydrochloric acid, I'm immediately going to get the salt, which is going to be KCl or NaCl along with water. So potassium will give me KCl, sodium will give me NaCl. Just ignore the sequence in which I put it. Alright. Similarly, if I take calcium, if I take magnesium, if I add HCl, or I can even also add H2SO4, I'm going to get the salt. If I use HCl, I'm going to get CaCl2. If I use H2SO4, I'll get CaSO4. Similarly, if I use Mg and HCl, I'll get MgCl2. If I use Mg and H2SO4, I'll get MgSO4. Along with this, I'll also get one hydrogen gas. Similarly, if I go into iron, or if I go into zinc and all of that, that will also give me a similar reaction. This is going to give me FeCl2, this is going to give me ZnCl2 plus hydrogen gas. However, the moment you go below hydrogen in the reactivity series, for example, if you take all weak elements such as copper, mercury, silver, platinum, etc., none of them will react with HCl or H2SO4 in dilute state simply because they cannot displace hydrogen from dilute acids. They all lie below hydrogen, so none of these reactions are going to work. So if you take copper, if you take mercury, if you take silver and all of these, none of them will react with dilute H2SO4 or dilute HCl because they lie below hydrogen in the reactivity series. Now that we have understood how it works with HCl and H2SO4, we all know these will cause simple displacement reactions. Let's move into how it works with HNO3. Now HNO3 is a very tricky acid simply because it can act as an oxidizing agent and in certain cases can also cause a displacement reaction. Now all of us at this point in time know that concentrated HNO3 is a very strong oxidizing agent. It is so strong that it can oxidize anything around it because it generates nascent oxygen in no time. Because of that, HNO3 tends to oxidize certain metals instead of causing a displacement reaction. For example, if I can just clear this, let's take an example of concentrated HNO3 or even dilute HNO3. First we'll start with concentrated HNO3. Copper, for example, we know does not react with dilute HCl, but copper reacts with dilute HNO3. So if you want to differentiate between dilute HCl and dilute HNO3, all you need to do is add copper. Wherever the reaction takes place, it is dilute HNO3. Wherever the reaction does not take place, it is dilute HCl. So let's look at concentrated first. If you take concentrated HNO3, then you're going to get copper nitrate, which is the salt, plus water, plus nitrogen dioxide gas. If you do the same thing with dilute HNO3, mind you, dilute HCl, H2SO4 will not react with copper, but HNO3 will. We give you similar products. It gives you copper nitrate plus H2O, but instead of NO2, you'll end up getting nitric oxide. So you're able to see, in this case, copper is getting oxidized to copper nitrate. Here also, copper is getting oxidized to copper nitrate. However, HNO3 is getting reduced to NO2. Again, HNO3 is getting reduced to NO. So this can also be termed as a redox reaction for your reference. Okay. Now, this is with dilute HNO3. Similarly, if you take very dilute HNO3, this is important from your examination point of view. If you take very dilute, sometimes it's called very dilute HNO3. If you take two metals, magnesium and manganese, both of them will react with very cold, very dilute HNO3 to produce magnesium nitrate, manganese nitrate, and in the process, they will release hydrogen gas. So a common question asked in the exam is, name two metals that liberate hydrogen gas with nitric acid. Your answer should be magnesium and manganese. Alright. Now that we have covered oxygen, water and acid, let's quickly finish off chlorine and hydrogen because with chlorine and hydrogen, the reactions are quite simple and I'm sure all of you will be able to understand it very quickly. I'll just do the chlorine and hydrogen reactions on the next slide. Let's look at chlorine reactions. Now, most metals are either present that we are going to consider are either present in group 1 or group 2 of the periodic table. Now group 1 and group 2 elements of the periodic table have very high affinity towards group 17 elements. Now chlorine being a halogen is a group 17 element. And since group 17 elements are excellent electron acceptors, group 1, group 2 are excellent electron donors, immediately exchange of electrons can take place, right? A metal can easily donate the electron, the non-metal can easily accept the electron. That's exactly what chlorine does. Chlorine immediately grabs the electron sodium can provide to it. So if you take sodium and if you make it react with chlorine, you're immediately going to get the salt, which is NaCl. And remember, these two are equal to being best friends. Similarly, when you take potassium, you make it react with chlorine, you're going to get potassium chloride. If you take calcium, make it react with chlorine, you're going to get calcium chloride. You'll have to balance all the reactions though, but these are the salts that are produced when metals react with chlorine. So if they ever ask you what is the product formed when metals react with chlorine, you're going to say it's corresponding salts. When it comes to hydrogen, now this is again a very interesting reaction. When you take sodium, when you take calcium, etc., and when you make it react with hydrogen, all of us know that hydrogen has a dual nature. It can act as a metal, it can also act as a non-metal. In this case, sodium and calcium being more metallic than hydrogen makes hydrogen act as a non-metal in this case. And since it acts as a non-metal, sodium with hydrogen will give you sodium hydride, and this is going to give me calcium hydride. So this is going to be sodium hydride, and this is going to be calcium hydride. Simple. Alright, with this, we have summarized the entire stop. With this, we have summarized the entire reactions of metals. Let's move into non-metals now. But before we do that, cut. With this, we have summarized the entire chemical properties of metals and non-metals. I'm just going to go back so that we just look at how each one reacted. Depending on the position of the metal in the reactivity series, they tend to react in different ways. Alright? We have, before we do that, cut. The entire chemical properties of metals and non-metals. I'm just going to go back so that we just look at how each one reacted. Depending on the position of the metal in the reactivity series, they tend to react in different ways. Alright, keeping this in mind, let us move into reactions of non-metals. Now we all know that in the first reaction that we did with oxygen, all these metal oxides that we get, Na2O, CaO, K2O, they're all basic in nature. Similarly, non-metallic oxides can also be acidic in nature, the opposite. So if I take the first reaction, which is reaction with oxygen, if I take non-metals such as carbon, if I take sulfur, phosphorus, nitrogen, etc., when they all react with oxygen, they tend to produce their corresponding oxides. Carbon and oxygen, when you heat, gives you carbon dioxide. We all know carbon dioxide is acidic because it tends to dissolve in water to form carbonic acid. So this will dissolve in water to give you carbonic acid. Carbonic acid is used in our fizzy drinks. Sulfur and oxygen together will give me sulfur dioxide. When sulfur dioxide dissolves in water, it forms sulfurous acid, which is H2SO3. Now a lot of students get confused and ask me, when does H2SO4 get formed? H2SO4 gets formed when SO3 dissolves in water. SO3 is called sulfur trioxide. Now how do you get sulfur trioxide? It's very easy. Just take sulfur dioxide, add a little more oxygen, but you'll have to use a small catalyst called vanadium pentoxide. If you add extra oxygen to this in the presence of vanadium pentoxide, you will get H2SO4 instead of H2SO3. P plus O2 together will give me P2O5, which is phosphorus pentoxide. When you add water to it, you're going to get its corresponding acid, which is phosphoric acid. And the last one, nitrogen and oxygen is a very tricky reaction. Nitrogen as such is quite inert. Nitrogen, because of its triple bond, is very hard to break. So what happens is, if you want it to react with oxygen, it has to react only in the presence of a very strong stressful factor. And the best way to make nitrogen and oxygen react is in the presence of a lightning strike. All of you have heard of nitrogen fixation in plants. This is exactly what happens. When nitrogen and oxygen react in the presence of a lightning strike, which I'm going to write as Ls, you're going to get nitric oxide. Remember, nitric oxide is neutral. When nitric oxide combines with more oxygen, it forms nitrogen dioxide. Nitrogen dioxide is acidic, and the way we identify nitrogen dioxide is through its reddish brown fumes. When NO2 is dissolved in water, it forms two types of acids. One is called HNO3, which is nitric acid, and the other one is called HNO2, which is nitrous acid. So if they ever ask you this question, name one non-metallic oxide that produces two acids upon hydrolysis. Hydrolysis means adding water. You're going to give nitrogen dioxide as the example. This is the first reaction with respect to non-metals. The second reaction with respect to non-metals is its reactions with chlorine, and that is mostly around phosphorus reactions. Phosphorus tends to react with chlorine. Now you can write P, or if you want to write it in molecular form, you can write P4. It is going to either give you PCl3 or PCl5 depending on the proportion of phosphorus and chlorine in the reaction. Now, if you use more chlorine, you're going to get PCl5. If you use less chlorine, you're going to get PCl3. Okay? And another important reaction we are going to look at, which is the last reaction, is reaction with hydrogen. Now, when it comes to reaction with hydrogen, hydrogen tends to react with chlorine to give you hydrogen chloride gas. But remember, for this reaction to take place, you need sunlight, because sunlight is the one that is going to activate chlorine. But keep one thing in mind, if you're going to use direct sunlight, it is going to cause an explosion, but the reaction is going to be rapid. If you use diffuse sunlight, the reaction will be slightly slow, but you will be able to see the reaction take place with safety precautions. However, if you conduct this experiment in complete darkness, there will be no reaction that is going to take place. The next one that we also have to understand is hydrogen plus sulfur. Okay, you heat it, you're going to get a very foul smelling compound which smells of rotten eggs called hydrogen sulfide gas. And the last one we have to also look at is when hydrogen reacts with nitrogen. And this is an important industrial method. This is also called Haber's process. This method can be used to prepare ammonia gas in the industry. Now, this nitrogen and hydrogen as such are quite inert, they don't react with each other very well. So to force them to react, you need to use a catalyst. Generally the catalyst we use is iron. To make the catalyst work better, we use something called as a promoter, which is molybdenum. The symbol is MO. You have to heat the reaction, okay, to about 450 degrees centigrade. Also apply a lot of pressure, about 200 to 900 atmospheres. So under all these conditions, you're eventually going to get ammonia gas. Now with this, we have successfully summarized the whole process of properties of metals and non-metals, starting from its definition to its physical and chemical properties. Alright, I hope you enjoyed this video. The second part of the video will talk about the metallurgical process, and with that you should be able to summarize the entire chapter. Thank you for watching.